Um, The topic we'll be discussing in this session is Banker's algorithm. So basically we are discussing about various deadlock avoidance algorithm. So there are two types of deadlock avoidance algorithm we have. One is using resource allocation graph and the other one is using Banker's algorithm. Resource allocation graph can be used as a deadlock avoidance algorithm if we have only one instances of all types of resource. But but if you have more than one instances of some of the resource or for all the resource, then we cannot go with resource allocation graph. In that situation, we should go for Banker's algorithm. So basically, Banker's algorithm is a deadlock avoidance algorithm. Also, we have one more algorithm, that is resource allocation graph. But resource allocation graph is for when the number of resources, when each type of resource we have only one instance. If if more than one instances of resource types are available, then we cannot go with resource allocation graph. In that situation, we should go with Banker's algorithm. So in this session, we'll be discussing the working methodology of Banker's algorithm, and also we'll be discussing some example like how Banker's algorithm works. So, so let us discuss some basic things. So before applying Banker's algorithm, there are certain things which is required. That is the process first. Every process should first tell the operating system that maximum how many instances of each resource type they will require. That it should be known to the operating system. Okay, so each process must claim the maximum resource uh, requirement of each type. So that we should know, that the operating system should know. Okay. Sometimes when a process requires a resource, it may have to wait. That may also happen because currently the operating system may not have that many resource, or the resource might have been held with some other process. So the process may have to wait until the other process releases the resource. And when a process gets all its resources, it must return them in a finite amount of time. So if a process needs X amount of resource and the operating system gave all the resources, then the process should ensure that it will complete the task within a finite time and it should return the resource. It should not take infinite time. So these are some of the pre-requirements of Banker's algorithm. Now let us see the data structures that were used in Banker's algorithm. So mainly Banker's algorithm use certain vectors and matrices. So what are those vectors and matrices that we will try to understand. So in whatever we are going to discuss here, n represents the number of process. So wherever we use n, the term n represents the number of processes, and m represents the number of resource types. M represents the number of resource type. I think you remember resource type. Resource type means different types of resource. It may be a hard disk. Resource type 1 may be hard disk. Resource type 2 may be a printer. Resource type 3 may be a scanner, like that. Okay? And each type can have multiple instances. Okay? So what are the various vectors and matrices the Banker's algorithm use? These are the data structures. Okay. So the Banker's algorithm use a vector called available. It uses a vector called available. If available of j equal to k, then what does it mean? If available of j equal to k means, it means that there are k instances of resource j is currently available with the operating system. Okay. There are k instances of resource type or j. There are k instances of resource. There are k instances of resource type or j is currently available with the operating system. That's what available of j equal to k means. So this is the first data structure. Available is the first data structure, which is a vector. Available of j equal to k means there are k instances of resource j is available with the operating system. The next data structure is a matrix max. The name of the matrix is max. It is a n cross m matrix. We know that n is the number of process and m is the number of resources. Okay. So, uh, so if the system contains 5 process and 6 resource types, then this will be a 5 cross 6 matrix. Okay. If the system contains 5 process and 10 resource types, then this will be a 5 cross 10 matrix. Okay. So, so here in this matrix, if max of I comma j equal to k, then it means that you know that n is number of process and m is the number of resources. Okay. So if max of I comma j equal to k, then it means that process I can request at most k k instances of resource type j. Process I can request at most k instances of resource j. So, so this is the meaning of max of I comma j equal to k means process I can request at most k instances of resource j. So this max the every process uh, should inform their max, should declare their max at the beginning itself to the operating system. That is like how many instances of each resource they will require. So that they will give us a matrix. Then the next data structure is allocation. Again, this allocation is also an n cross m matrix where n is the number of process and m is the number of resources. If allocation of I comma j equal to k, if allocation of I comma j equal to k, then it means that k instances of resource j is allocated to process I. Means that k instances of resource j is allocated to process I. Okay. So that is what is called as allocation. And there is another data structure which is need. So this is also a matrix, n cross m matrix, where n is the number of process and m is the number of resource types. If need of I comma j equal to k, if need of I comma j equal to k, then it means that the process pi, then it means that the process pi needs k instances of resource j. Okay. So then it means that the process pi needs k instances of resource j. Okay. And one more thing, need of I comma j will be always equal to need of I comma j will be always equal to max of I comma j minus allocation of I comma j. Okay. Because need is max is what maximum ith process needs how many instances of resource type j, that's what max. And allocation of I comma j is what currently the process I is allocated with k instances of resource j. So what is need? So need is how many it needs more. How many it needs more is it's nothing but max minus allocation. Okay. So need of I comma j will be always equal to max of I comma j minus allocation of I comma j. So these are the data structures that were used in the Banker's algorithm. So basically there is one vector and 3 matrices. The vector is available, which represents how many resources, how many instances of each resources are currently available with operating system. And 3 matrices, max, allocation and need. Max, for each process it represents how many instances of each resource type each process will require. And allocation represents how many instances of each resources were currently allocated to each process. And need represents how many instances of each resources will be required in future by each process. And always need of I comma j will be equal to max of I comma j minus allocation of I comma j. Okay. So these are the data structures that are used in Banker's algorithm. So with this knowledge, let us try to understand the Banker's algorithm. So Banker's algorithm is basically given by two algorithms. One is a safety algorithm and the other one is a resource request algorithm. So first let us discuss the safety algorithm. So in safety algorithm, we use two vectors. These are work and finish. These are work and finish. And these vectors are of length m and n. Okay. So work basically represents the resources. Okay. So the number of resources is m, and finish represents the number of processes. Okay. So basically finish represents how many process has been completed so far. And work, the length of work is equal to m, which is nothing but the number of resource types. So the first step what we do is work is equal to available. What is available? You just recollect. Available is a vector. In the previous slide we have discussed. Available is a vector of length m, that is of number of resource types. If available of j equal to k, then it means that currently k instances of resource j is available with the operating system. Currently j instances of k instances of Currently k instances of resource j is available with the operating system. So basically available is a vector which represents like how many instances of each type of resource are currently available with the operating system. That's it. It is as simple as that. How many instances of each resource types are currently available with the operating system. That's what this vector available contains. So we are just assigning available. We are just assigning the content of available to work. So now work also contains the same thing. Okay. Now work also contains the same thing whatever available contains. So available contains how many resources of each type are currently available or free to use. Similarly, work also contains the same thing. Work also contains how many resources, how many instances of each resource types are currently available. Okay. And then what we do, finish of I. So finish is a vector of length n. So if there are n processes, then for all n processes, we are setting finish of I is equal to false. For all I equal to 1 to n minus, for all I from 0 to n minus 1. Okay. Processes are numbered from 0 to n minus 1. Because initially none of the process was completed. So initially we are setting finish as false. So this is the first step in safety algorithm. This is the initialization step. What we are doing is we are just assigning available work equal to available, which means work will have the same thing as available. So available contains like how many instances of each resource types are currently available with the operating system. Now work will also have the same thing. And we are initializing all contents of finish as false, which means that none of the processes has completed it. Then the second step of the algorithm says that find an I such that find an I such that both of these conditions were satisfied. Okay, find an I such that both of the following conditions were satisfied. What are the conditions? Finish of I should be false. Finish of I should be false. Okay, and need of I should be less than or equal to work. Work means what? Work is nothing but currently available free resources. Okay, because available is assigned to available, work is assigned to available. So what are the resources currently available with the operating system? That is what work is. So it will check two conditions. One is finish of I should be false. Finish of I is obviously false for all processes initially. Then it checks whether need of I is less than or equal to work. What does it mean? It means that say the first process, let us start with 0. If I is 0, then for the 0th process, how much resources it needs more is less than the available resources with the operating system. That's what it checks. Because if there is no available resources, you cannot allocate. For example, say need of I is need is I need 4 hard disks, but currently operating system has only 2 hard disks. Then how it will give? In this case, need is greater than work. Work is nothing but available. Okay, I need 2 hard disks. Operating system has 5 hard disks. In this case, need is less than work. In that case, it will give. Okay, so we are checking both the conditions, whether finish of I is false. If finish of I is false and need of I is less than work, then 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 what should we do? Then it will execute step 3. Then it will execute step 3. What is step 3? Work is equal to work plus allocation. Okay, let us understand this point to further. If need is less than work, say I need currently 2 resources of printer or hard disk, whatever it may be, and operating system is having 5, that is work. So need is less than work. So it means what? So if need is less than work, then the operating system can give that to me, to this process, whatever the process request. Okay. So the operating system will obviously give this two process. It will allocate two process. Okay. To the sorry, it will allocate 2 hard disk to the process P naught. It will allocate 2 hard disks to the process P naught. Now what P naught will do? P naught will obviously use these 2 resources, that is 2 hard disk it will use, and it will complete the task. It will complete the task. After completing the task, what P naught will do? P naught will obviously, after completing the task, will release the resource. Okay, will release the resource, right? So so that is what. See, the point here is, if need is less than work is nothing but available. If need is less than work, then the operating system can give all the resources whatever that particular process is requesting. If the resources were given, then the particular process will use the resource and it will complete the task. After completing the task, what that process will do? It will release the resource because no more it needs the resource. Okay. Then once again, what will happen to work? Work will be equal to work plus allocation. Work will be equal to work plus allocation of I. What does it mean? Because ith process, whatever it needs, you have allocated. So now ith process has completed its work. So after completing, it will release all the resources that it was allocated to it. All the resources that were allocated to the ith process will be released. So work will be incremented by whatever the number of processes that were previously allocated to I. Okay, because previously you gave that many processes, and using that you gave that many resources, and using that resources, the process Pi has completed its task. Okay, so now the particular process I process has finished. So finish of I is equal to true, and again go to step 2. Keep on repeat this. Keep on repeat this. So this will keep on repeat how long? Until all finish of I becomes true. Until all finish of I becomes true, and there is no need of I which is less than work. Okay, until all finish of I becomes true, it will repeat. Okay, if all finish of I becomes true, that is, if this algorithm is unable to find an I such that finish of I is equal to false and need of I is equal to work, both the conditions should be satisfied. If it is unable to find such a process, then it will go to step 4. What is step 4? Step 4 is it will check whether finish of I is equal to true for all I. Then the system is in the safe state. The system is in the safe state. So this is how the safety algorithm is defined. So similarly, there is another algorithm which is called as resource request algorithm for the process Pi. Okay. So in this algorithm, we use something called as request I of j equal to k. request I of j equal to k, which means that process I is requesting here the subscript I near to the request. Okay, it refers to process pi. Okay, so it means that request I of j equal to k means process pi is requesting k instances of resource type rj. Means that process pi is requesting k instances of resource type rj. Okay, with this knowledge, let us go through the algorithm. The first step says that if request of I is less than or equal to need, go to step 2. Otherwise, raise an error. Because request should be always less than need. A process cannot request something which is more than need. Okay, request should be always less than or equal to need. Because what is need? Max, you are defining max. Max contains what? Initially, we are telling max. Every process should declare its max. Max is nothing but how many instances of each resource a particular process will require. And then there is allocation. What is allocation? Allocation is how many instances of each resource were allocated to a particular process. And need is nothing but max minus allocation. So how many they need in the future. So that can be calculated from max minus allocation. And if any process requests any new resource, if any process requests any further resource, surely it should be less than or equal to need. It cannot exceed need. If it exceeds need, then it is not following the commitment which is given by the particular process earlier. Because before starting, every process should declare what is their max. It is maximum how many instances of each resource type they will require. That should be declared. So according to that only the request happens. So whenever the request is less than or equal to need, then we can proceed. Suppose if request is greater than need, then it means that there is an something wrong. So the algorithm will not continue. It will just raise an error condition. That's the first step. Next, you have to check. First, you have to check whether the request is less than need. If request is less than need, go to step 2. Otherwise, raise an error. Next, in the step 2, check whether request is less than available or not. Okay, request is less than need. Then you check whether the request is available, less than or equal to available or not. Available represents currently how many instances of each resource types are available with the operating system. And request should be less than that. Then only the operating system can offer those resources. Otherwise, it cannot offer. Okay. So here, if request is less than or equal to available, then go to step 3. Otherwise, process PI must wait. How long it wait? Until request becomes less than or equal to available, it should wait. Okay. Because if it is not available, how the operating system will give? So if both these conditions were satisfied, if request is less than or equal to need, and if request is less than or equal to available, then we will go to step 3. What step 3 says in the sense, step 3 of Banker's algorithm, what it says in the sense, it is quite interesting. It does not ask the operating system to just allocate the resources to the process PI. What it says in the sense, it asks the operating system to pretend to allocate the resource PI by modifying the following states. What are the states? So let us assume that, okay, if these two conditions are satisfied, it means operating system has sufficient resource to satisfy the request raised by this particular process. But now the process is not going to directly allocate, but before allocating, it is just going to make some calculations. It is going to act as if it is allocated, and then it is going to see what will be the uh, what will happen if it is allocated. Okay, so if this request was satisfied, then what will happen? Then obviously available will become available minus request of I, because ith process has requested this. So previously whatever the available, that will be subtracted, and allocation will become allocation plus request. Okay, because already some resources were allocated. Now some more resources were also added. So allocation will become allocation plus allocation uh, for ith process will be equal to allocation of ith process plus request made by the ith process. And need will decrease. need of I will become need I minus request I. Okay. So after making these changes in the following in these states, the operating system should check whether this is a safe state or not. Whether after making these changes, will it lead the system in the safe state or not? That it has to check. If it will lead the system in the safe state, then you allocate the resource. Then you allocate whatever the resources that were requested by PI, just allocate those resources to PI. Suppose after making the changes, if the operating system observes that no, this will not make the system in the safe state, it will take the system to unsafe state, then the process PI must wait. And whatever the request that process PI has requested for, that cannot be granted. And it will, and the resource allocation state will be restored. That is, it will go back. This will not be taken. Whatever the previous state will be considered. Okay. So this is what the banker's algorithm does. So basically there are two algorithms. One is safe algorithm, the other one is resource request algorithm. Now let us try to understand banker's algorithm with an example. Say we have 5 processes which are numbered from P0 to P4. There are 5 processes which are numbered from P0 to P4, and there are 3 resource types available with the operating system. There are 3 resource types available with the operating system. These are resource A, resource B, and resource C. There are 10 instances of resource A, 5 instances of resource B, and 7 instances of resource A. Okay, so this is the available with the operating system. So this represents the how many resources are available with the operating system. We have discussed many data structures. Out of the first data structure is available. So this is what the available data structure shows. And this is the allocation. Currently, this is how the resources were allocated to various processes. So as we discussed, there are 5 processes P0 to P4. That is, 0 instances of resource A is allocated to P0, and 1 instance of resource B is allocated to P0, and 0 instances of resource C is allocated to P0. Similarly, 2 instances of resource A is allocated to P1, and 0 instances of resource B is allocated to P1, and 0 instances of resource C is allocated to P1, and 3 instances of resource A is allocated to P2, and 0 instances of resource B is allocated to P2, and 2 instances of resource C is allocated to P2. Like that, these many resources were allocated. Okay? And this max represents maximum how many resource each process, how many instances of each resource each process will require. So it means, so this means P0 will require maximum 7 instances of resource A, and maximum 5 instances of resource B, and maximum 3 instances of resource C. And P1 will require maximum 3 instances of resource A, and maximum 2 instances of resource B, and maximum 2 instances of resource C. So that's what this max matrix says. So we know already max is a matrix, allocation is a matrix. Okay, available is also a matrix. Now available is what? Available is nothing but currently available is what? So originally available with the operating system is 10 instances of A, 5 instances of B, and 7 instances of C. This is the total available resources of in the operating system. Total available instances of each resource types in the operating system. But here some of them were already allocated. If you take resource A, if you take resource A, 2 instances were allocated to P1, 3 were allocated to P2, 2 were allocated to P3. So already how many gone? 2 plus 2, 4, 4 plus 3, 7. 7 instances of resource A already allocated. And operating system has how many? 10. So 10 minus 7 is 3. So remaining available is only 3. Okay, this is originally available, total available resource with the operating system, but currently the resource type A, we have only 3 instances because remaining 7 were allocated to various processes. Similarly, if you check for process B, already how many allocated? 1 for P0 and 1 for P3. Total available resource is 5. So 2 were allotted. So 5 minus 2 is 3. So the available current available of resource B is 3. Similarly, C, if you see, total available is 7. Currently, 2 instances of C was allocated to process 2 and 1 instance was allocated to process 3 and 2 instance was allocated to process 4. So 2 plus 1, 3, 3 plus 2, 5. 5 instances were already allocated. So 7 minus 5 is, so the remaining available resource is 2. Okay. So this is what this particular chart shows. Okay. So this is the current state of the system. This is the current state of the system. Now let us say that, so now what, from this we can calculate need. From this we can calculate need. How we can calculate need? Need is always what? Need will be always max minus allocation. Need will be, already we discussed, max minus allocation. Okay. So need of P naught will be what? P naught will require maximum 7 instances of resource A, but 0 is allocated. So P naught, so need is what? Max minus allocation. So 7 minus 0 for P naught, the need will be, if you put need here, if I put need here, just for explanation purpose, okay, for P naught, how many instances of resource A it may require in the future? It is just max minus allocation. 7 minus 0 is 7. It needs all 7 because none of them was allocated. For B, max is 5 and allocated is 1. So 5 minus 1 is 4. It may need 4 instances of resource B. And for C, max is 3 and none is allocated. So 3 minus 0 is 3. Okay. So 743 will be the need for P naught. Like that, you can calculate the need for other processes also. Okay. So need for P1 is 3 minus 2, 1, 2 minus 1, 2 minus 0 and 2 minus 0. So it is 1, 2, 2. Okay. So like that, the need vector is calculated. Okay. So now let us check whether this is a safe state or not. Yes, this is a safe state because there exists a safe sequence. There is a safe sequence P1, P3, P4, P2, P0. In this order, if it executes, then all the all the resource request of all the process can be satisfied. So this is, so there exists a safe sequence. Here there is a safe sequence. Okay. So this is, so this is a, the currently the system is in a safe state. Okay. Hence you remember the definition of safe state. The system is in the safe state if there exists a safe sequence such that the resource request of all process Pi can be satisfied from the available resource plus the resource that were currently held by Pj, okay, where j is less than I. Okay, fine. Now let us assume that process, now let us consider one particular scenario where process P1 is requesting. So this is a request. This is a request which is coming from process P1. This is a request which is coming from process P1. Process P1 is requesting 1 instances of resource A and 2 instances of resource C. Okay. Process P1 is requesting 1 instance of resource A, 0 instance of resource B, and 2 instance of resource C. Okay. So first what we have to check whether the request is less than or equal to available or not. That we check. Available is what? First you have to even match with need. Okay, whether the request is less than need or not as of the algorithm, because the algorithm says what? First you have to check whether the request is less than or equal to need or not. What is the need of this is P1. Okay, this is uh, this is P1. So P1 is requesting 102. Okay. So P1 is requesting 102. So let us go to the previous graph. Okay. So the need of P1 is what? 122. Need of P1 is 122, and what is it is requesting 102. So 122, is it less than or equal to 102? That's what you have to check first. Need. Okay. Yes. 122. Sorry. 122 is the need, and request is 102. So you have to check whether 102 is less than 122 or not. Request is 102. Okay. So this is less than or equal to 122 or not? Yes, this is less than or equal to 122 because 1 is equal to 1, right? 0 is less than 2, 2 is equal to 2. So this is less than need. Fine. So less than need means you go to the next step. The next step you have to check whether it is less than available or not. Okay, it is less than available or not. What is available? In our case, in this previous case, the available is 332. Available is 332. And need and what it is requesting 102. Yes. So 102 is again less than or equal to 332. So it is available. Okay, so its request can be satisfied. What is the request? It is asking one more instances of A and two more instances of C. Okay, so here you can see currently it is 202. So it is asking one more instance of A. So this will become 1. Sorry, this will become 3, and two more instances of C. Okay, so this will become 2. Okay, so it will become 302. It will become 302. And what will happen to available? This 3 will become 2 because it has given one resource from available was given to P1, and this 2 will become 0. Okay, so that is how here we got 230, and here we got 302. Okay, so now this request from P1 is satisfied. So but we will not satisfy just like that. The operating system, before giving, it will check whether there is a safe state exist or not. Operating system will pretend as if this resource was allocated, and then it will check whether there exists a safe state or not. Yes, here there is a safe sequence P1, P3, P4, P0, P2. Okay, you can check. What is P1? P1 needs 020. What is available? 230. So this is less than available. So obviously this, if you give now if you satisfy all requests of P1, now P1 will complete. P1 will complete, and also it will give back all its held resources. What are the held resources? It is holding three resources of R1. Okay, sorry, resources of A. So if it release that, it will become 5. A available will become 5. And it is holding two resources of B. If it gives that, B will also become 5. And it is holding two resources of C. So if it gives that, it will become 2. So if P1 is completed, then next you can give to P3. P3 needs only 0, 1, 1. Okay, then if P3, then if you give this 1, 1 to P3, then P3 will be completed. Then P4 will be completed. Like that, there is a safe sequence. Okay, so this request can be satisfied. So here there are two questions which you can work out whether the request 330 by P4 can be granted or not from the current state. So this request cannot be granted because here you see P4 is 431 where available is 230. So the request is 330. The request is 330, but the available is 230. The request is not less than available. So this request cannot be granted. Okay. Can the request 020 by P0 be granted or not? If P0 request 020, can it be granted or not? If P0 request 020, 020 is less than available. Yes. So it can be granted provided if there is a safe sequence. Okay. It can be granted provided if there is a safe sequence. So the operating system should pretend as if it is granted, and then it should check whether there is a safe sequence or not. Okay. you can check and tell whether there will be a safe sequence or not. Okay. I guess there will be a safe sequence for this, right? So this is about Banker's algorithm. This is a deadlock avoidance algorithm, right? So this algorithm will be used when there are more instances of more than one instance of each resource type. Okay, fine. Thank you.